Hello, AP Physics 1, this is Mr. Ng, and I have prepared a little lesson on sheets. This is not to teach you sheets. This is basically to cover some of the misconceptions and misunderstandings that I caught during this lesson today and just during the week. I need to just admit that many of you need these clear numbers, and I think I've been a little unclear. And I think if I just showed you some real numbers, you could see how velocity, acceleration, and displacement work, right? So as you can see, our example is about a ball. And I want you to imagine someone really strong, like the Hulk or something, bounce this basketball because it's going to go really high up. It's going to go like 100+ meters up into the air, right? And I notice our initial parameters here. We have a position of 0, meaning this is right on the floor, an initial velocity of 50 up. It's going to go up by 50 meters per second. Now, when I say it goes up by 50 meters a second, some of you might be tempted to think that there's some sort of force acting on it. There was right when it bounced, but then that's it. That instant and that's it. So don't think about some sort of residual force on it, right? In our unit on kinematics, we're just kind of following the path of this motion, and there are no outside forces acting on it. In fact, if there were outside forces acting on it, we won't be able to use the equations that I will be showing you in the next couple of weeks. So here, it's moving up at 50 meters per second, right? None of this kind of residual, like more energy on it. It's not like being propelled forward by some invisible force, right? It's being propelled forward just by the inertia of its movement, okay? And then finally, gravity is acting down on it by 10 meters a second. Good? So let's try to fill out this table based on what we know. The easiest column that we could fill out is gravity. It's always going to stay at -10, so let's drag that down. So gravity is always at -10. Once we know that gravity is always at -10, we can figure out that velocity is going to change, and it's going to change by -10. So in the at the 0 second, the velocity was 50 up. The next second, gravity worked on that initial velocity up, slowed it down by 10, so now it's only 40 up, right? And next, it's going to be 30 up because each second it's losing a velocity of 10. Does that make sense? So really the equation here is just equal to the last velocity plus this acceleration, which is -10 at this point. So it goes to 30, then 20, then 10, then 0, so on and so forth. After 0, it starts to go down, and at first it's a little slow going down, but the more time you give it to go down, the faster it goes down because gravity is helping it go down faster. It's accelerating its path downward, right? Notice that the negative means that it's going downward and the positive means it's going upward, right? Just in relation to whatever we set the initial position to. Good? So now the last thing we got to do is we got to figure out their positions. So in the very first second, this thing was traveling up by 50 meters per second. That means after a second, it's at 50, right? The next second, it's going up by 40. So it was at 50, now it's going to go 40 up, plus 40. So the equation here is this one plus the velocity next to it. So 40 up is 90, right? 90 and 30 becomes 120, becomes 140, so on and so forth, until it starts to go down, right? It goes all the way up to 150. Notice how it slows down. It goes up real fast by 50, by 40. Up here, it kind of slows down right at the apex, and then it starts to speed up again as it comes back down. Good? Let's get rid of this basketball picture. Get out of here. And let's look at the actual graphs. Okay, so let's just insert a chart. Right, so this is what it kind of looks like. I'm going to smooth it out just so it looks a little bit nicer. Okay, there we go. That looks nice. Okay, so here, notice that the position chart is just a parabola. The velocity chart is a straight line that's not flat, and the acceleration is flat. right? This is kind of a classic setup that you will need to kind of memorize in physics, that when there is a constant acceleration, right? Notice that this acceleration is at -10 and it's horizontal. Then the next order up would be a diagonal, right? In this case, it's going down. The slope is negative, that it's going down. This is the velocity down. And then the displacement becomes a parabola, okay? So this is kind of the pattern that you should notice and you should see. So now let's go back to that kind of summary table that many of us struggled with. And you know what? I didn't do you guys any favors. I asked things that were suggestive, and maybe you thought that you should say one thing versus another, and my instructions might have been a little bit unclear. So let's clarify that. So here, this is the summary chart that we had today. The x-axis, man, I should not have asked about the x-axis, because I wrote that the x-axis was the initial position, and it usually is, because we assume that many things start at 0. But what if we thought about the motion while the ball was already in the air? Then the x-axis would be meaningless, right? Or what if there was a trench and the ball went farther down? Then the x-axis means nothing. So really the x-axis just means a position at 0, right? For displacement graphs, right? For the velocity graph, that's something completely different. For this velocity graph, when this velocity graph hits the x-axis, right, when the velocity is at 0, that means this thing is at the apex of its path. That means the ball went to the very top, and when it hits the x-axis, that means it's at 0, right? Velocity is 0. That means it stops. So this means that this thing stopped, right? The y-intercept, this is just the initial position right here. That's for both. Initial position. The slope of the tangent of a displacement time graph. Okay, so the slope here is high. It gets slower and slower until it's horizontal. The slope of this displacement graph refers to the velocity. That seems easy enough. And the slope of this velocity time graph, this slope, right? This slope, if you do the math, is going to be -10, which is basically -10 is our acceleration. That's easy, right? What if we had a positive slope for our displacement graph? What if we had a positive slope for the blue lines? Well, everything on this side, right, from 0 to 5 seconds has a positive slope because it's moving up, right? It's moving in the positive direction. And it has a negative slope, then it's moving in the negative direction. So in this case, it's moving down, right? So positive slope means moving in the positive direction, whatever you designate that to, usually up or to the right, right? And this is moving in the negative direction. Fine. For the velocity, if it has a positive slope, then that means it's getting faster and faster. It has a negative slope, that means it's going slower and slower, or moving more and more down, right? So here, a positive slope, that's with the basketball. For the velocity time graph, a positive slope would mean this line is going up. That means the acceleration is positive. If you have a negative slope, that means the acceleration is negative. So here, positive acceleration. And here, this means negative acceleration. Be very careful here. I bet some of you might think positive acceleration as in like a larger magnitude of acceleration. But when we say positive acceleration, we mean that it's moving on the positive side. So in this example, positive acceleration means moving up, accelerating up. And a negative acceleration, which is what we have, means moving or changing the velocity downwards, right? So be careful about that. Don't think of it as bigger or smaller. The positive or negative is about directions in the positive side or the negative side. Okay. Here, a zero slope for the displacement graph. Well, zero slope occurs right at the very top here, and that happens basically when it stopped moving. And here, a zero slope here means that there's no velocity, right? I mean, there's no acceleration. Okay, that means like every now and then we might have a velocity line that's just horizontal with a zero slope. That means a constant velocity. Okay. Straight lines in a graph like this. So our displacement graph is curved, but if it had a straight line, then that means it has a constant velocity. If the velocity time graph is straight, which is what we have here, that means we have a constant acceleration. So in our class, we will almost always deal with constant acceleration, just so you know. A curved line in the displacement time graph means that we have some sort of, like a moving velocity, like a velocity that's an angled line. All right. You have a velocity. And then here, a curved line means that we have a changing acceleration. Just velocity, that's dumb. Changing velocity. And then finally, when do we know it stops when it's a displacement time graph? Well, when the slope is 0. And when do we know it stopped in a velocity time graph? When it crosses the x-axis. Meaning when y is equal to 0. Okay, I know this summary table was a pain for me to get through. I bet some of you just skipped to the end until you saw it, which is cool. I hope that clarifies a lot of things. Don't be afraid to ask me questions. Really sorry for the super long video. And I hope this clears up some of those misconceptions that we have, or some of the confusion that we have. I'm here for you, so please ask me questions. I'm around after school most days. And thanks for watching, guys. I really appreciate how hard you've been working.